Imagine trying to calculate the total twisting force exerted on the surface of an object by its own position relative to a central point. In physics and geometry, this is often represented by a specific type of calculation called a surface integral of a cross product. Specifically, we are looking at how a position vector, an arrow pointing from the center to any point on the surface, interacts with the direction the surface is facing at that exact spot. The mystery of the vanishing twist. When you perform this calculation for any closed surface, such as a solid ball or a sealed can, the final result is always exactly zero. To understand why, we can look at the space inside the object instead of just the surface. A mathematical rule allows us to transform this surface calculation into a measurement of the swirl or rotation within the enclosed volume. As it turns out, the position field, the collection of all arrows pointing directly away from the center, has absolutely no swirl. Because these arrows only move straight outward, they never create the kind of circular motion or curl needed to produce a non-zero result. When you add up zero swirl across the entire volume of the object, you end up with a total sum of zero. Visualizing the balance. Demos 1 and 2. To see this in action, imagine an interactive simulation of a sphere or a cylinder. Demo 1. On these shapes, you can pick any point and see three arrows. One pointing from the center to the point, one pointing straight out from the surface, and a third representing their interaction, the cross product. On a symmetrical shape, this third arrow always lays flat against the surface. If you add up all these flat arrows across the whole shape, they perfectly balance each other out. Demo 2. Another visualization shows a cloud of arrows radiating outward from a single point, like a starburst. Because every arrow is perfectly perpendicular to the surface of a surrounding sphere, there is no twist at all. This visual symmetry is the reason the final calculation vanishes. When symmetry breaks. The open surface example. The story changes if the surface is open, like a bowl or a flat coin, rather than a closed container. In these cases, the result depends entirely on where the edges of the surface are located. Demo 3. The centered disk. Imagine a flat, circular disk perfectly centered at the origin. The arrows representing the twist form a perfect circle around the center. Because the disk is centered, every arrow on the left is cancelled out by an identical arrow on the right. The total sum remains zero. Demo 4. The shifted hemisphere. Now, imagine a bowl that has been pushed away from the center point. Because the bowl is no longer centered, the position arrows on the far side are much longer than those on the near side. This breaks the balance. The push from the far side is stronger than the push from the near side, and the arrows no longer cancel out. The result is a non-zero value that points in the direction the bowl was shifted. A physical intuition. The torque analogy. A helpful way to think about this is through the concept of torque or leverage. If you imagine a uniform pressure pushing against the surface of an object, this calculation tells you if that pressure will make the object rotate around the center. A closed shape or a centered bowl is in perfect balance. The pressure on one side is countered by the pressure on the other, so it doesn't spin. A shifted bowl, however, has more leverage on the side further from the center, creating a net twisting force that would make it want to rotate. Ultimately, while the math tells us that closed shapes are always perfectly balanced in this position field, open shapes reveal how the displacement and boundaries of an object create unique physical forces.